Thank you for watching, ladies and gentlemen. This is Mark Anderson from Kellogg Community College. We're going to be talking today about Chapter 2, Section 4 of Trigonometry, which is going to be drawing and graphing trigonometric identities using transformations. Now, what I have here at the top of the page is I have just two cycles or two periods of a sine wave here. Now, this is the sine of x. This is the sine wave x as x and y axis. So this is the y position, and then this would be the the height of the curve based at any given time x, and this x would be marked at every half pi interval, because on a sine, if you looked at the y values on your unit circle basically in the first and second quadrant, you're going to see at 90 degrees it's at 1 on the y-axis, and then back to 0 again. And then at 270 degrees, it's going to be at -1 height on your y-axis when we have 3 pi over 2. And then back when we get to 2 pi, we're back to 0 again. So on the unit circle, if we go around in a counterclockwise fashion, the y starts out at 0, goes up to 1, then back down to 0, and that's marked right here. And then as we go to 270 degrees, or 3 pi over 2, it goes back down to -1 and back up to 1. So this constant counterclockwise rotation takes the dot up and down along the height-wise along this line. So this is 4 pi over here, and this would be 3 pi. And so you'd see that every half pi you'd be oscillating between 1 and -1, since our unit circle's radius is 1. Now this is, I should probably have that equal to y. This is our cosine of x right there, and that's my y right there, the y-axis. This is my x-axis, and you'll notice that within one period or revolution, it starts at 1 and goes all the way down to -1 and back up to 1 again. So again, if we look at the unit circle starting at 0 degrees, our x value, because cosine is our x value along the unit circle, starts off at 0, and then by the time it makes it, starts off at 1, because this is the point 1 comma 0, and by the time it makes it to 180 degrees or pi units, it's at -1 comma 0. So you can see that the unit circle is going to start off with this point at 1, and then in 180 degrees will be at -1, and then back to the start of the unit circle, it would be there at +1 again. So you can see that this is two cycles of the cosine wave all the way to 4 pi, and these will go on forever and ever and ever as in terms of units of pi. So these domains are all real numbers, are between -infinity, +infinity, and its range is going to be however high the graph is. In this case, it's going to be between -1 and 1. We want to take a look, move this down a little bit, and have you draw maybe your first sine or cosine wave. Let me make sure I get all these questions in here. Drawing your first sine and cosine wave, what I'd like you to do is maybe start off a little slower. So instead of considering this to be pi, we're going to consider, or this to be, 2 pi, we're going to call this just pi right here, and this is 2 pi. This way we're going to get a little bit of room for you to write your first sine of x. Now if you take a look at the unit circle, the y value at 0 degrees is 0. But your y value at pi over 2 is 1. So at pi over 2, the height of your y is 1, or at 90 degrees. Then at 180 degrees, it's at 0 again. And then at 3 pi over 2, which is at your 270 degrees, your dot is back to -1. And then here, back at 2 pi, we have 0 degrees. So, of course, if you take a look at this on the unit circle right here, here's your start. Pi over 2 is at a height of 1, pi is at a height of 0, and then 3 pi over 2 is a height of -1. So that's where we get this beautiful curve right here, like so. Alright, now we're going to look at this cosine of x, and we're going to do the same thing. We're going to have pi and 2 pi. We're going to draw one cycle here. So pi over 2 and 3 pi over 2. And we'll draw a unit circle like so. Okay, and we'll notice that at the start, my x value is at 1, so there's my start at 1. If I move to 90 degrees right there, I am going to be down to 0 on my x. Move to the 180 degrees there, I'm at negative 1 on my x, and then right here at 3/2, I'm back to 0 again, distance from 0. And then at 2 pi, I'm a distance of 1, so that's where I have my cycle like this. Now I'm going to keep these up here a little bit and show you just a couple questions that are out of the book. These are problems 9 and 10, and I modified them a little bit. The y-intercept of the sine graph, because this is going to deal with the sine, and this is going to deal with the cosine. So the sine graph right here, the y-intercept is going to be 0, 0. For what numbers between negative pi and pi is the graph of f increasing? So if I extended this graph out to negative pi, so there's negative pi on my x-axis here, when is f of x increase, or when is the graph of f increasing? It's actually increasing from this negative pi over 2 all the way up to this positive pi over 2. Because if you go back all the way to negative pi, which is all the way over here, this is going to be decreasing. So between here and here, or between the set of x, where x is between the negative pi over 2 all the way to pi over 2, this is when it's increasing. You'll notice that I didn't put in any lines underneath these, and I didn't do that because I didn't want to have to include those little flat spots at the top and bottom. The absolute minimum of f is negative 1, and if I was going to go through one cycle, when does f of x equal 0? It equals 0 at 0, pi, and 2 pi. Now from negative 2 pi to 2 pi, when does f of x equals negative 1 or 1? Well, let's take a look here at just the positive side of it, and then we'll kind of flip it for the negative. So if I want to find out when will the height be negative 1, I can see that here at positive 3/2, 3 pi over 2 for my x. But in the negative zone, if I had to figure out when it was there, it was at negative half pi. So that's when I hit my x or my y value of negative 1. Now if I go to my f, when is f of x going to be a height of 1? Like when is it going to be there at the top? Well, that's going to be, I can see that from right there, it's going to be at an x value of pi over 2. And it's going to be also, if I went back further enough, it'd be at negative 3 pi over 2. What are the x-intercepts of f? That's the x-intercepts is right. Actually, we kind of answered that right here in part D. The x-intercepts of f are at 0, 0, pi, 0, and 2 pi, 0 in this problem right here, or basically every k pi where k is an integer. All right, let's look at number 2. Number 2 says, what is the y-intercept in this graph? The y-intercept is actually 1, 0. It says between negative pi and pi, so if I went down to negative pi there, so here's my negative pi on my x, so I'm going between negative pi and pi. When is graph of g decreasing? And it's really decreasing between here and here. So in that set right there, x is decreasing between 0 and pi. Don't put in the less than or equal to symbols because we don't actually want those flat spots right there, because then it would be 0. Absolute minimum of g is negative 1. When does g of x equal 0? So when does this, we were talking about x-intercepts here. Where is the x-intercepts, or when does it land at 0? It lands at 0 at pi over 2. It also lands at 3 pi over 2. For what numbers we got negative 2 pi to positive 2 pi here. because we'll imagine that there's another cycle of this right here. When does g equals -1 or 1? Okay, well, let's take a look when it equals to -1. We can see this on the graph. When does this flat line down there? Looks like it flatlines at, we flatline at the -1 at pi. You can see that. And then 180 degrees before, we flatline at -pi, because we can see that down there, -pi. And therefore, we're going to hit our top of the grid right there, top of that line. We're going to hit that at 0 and at 2 pi. That also means we'll hit it at -2 pi. Now it says compare the x-intercepts from f of x to g of x. Now what's neat about the comparison is that if you look at these two graphs and you look at the x-intercepts, they're actually shifted. So it's funny that the cosine is actually a shift of the sine. So since the cosine is a shift of the sine, it's actually a shift to the right or to the left by only 90 degrees, or by a factor of a pi over 2. These are considered sinusoidal, excuse me. And these sinusoidal graphs are built off the sine wave, which is this graph on the left. So if we just shifted this graph here by subtracting pi over 2, you could see that the cosine graph is nothing but the sine graph shifted basically part of a cycle. Actually, pi over 2 parts of a cycle, or a quarter of a cycle. And so we're going to take a look at just a little bit more of this before we take this away for the end of part 1 here. So let's go to our next page. And we're going to talk about amplitude and period. Now what's kind of interesting is I want to take a look at the idea of what is amplitude. Amplitude is a volume. So if this left-hand side here, we're going to be using this as for our amplitude, and the right-hand side, this is going to be for our demonstration of period. Now I'm going to move this worksheet down just a little bit so I can get the bottom of these axes in there, so you just lost the top of the directions. Again, we're going to talk about amplitude because let's imagine that instead of this being a 1, let's make the top and our bottom of our grid here. Let's make the middle a 1 and a 1, and let's put in a sine of x. This is a sine wave, and we know that sine waves, and we're going to make this one cycle right there to 2 pi, and this is going to be our sine wave, like so. Now you notice that we have room to grow in the top and bottom here. So this dot represents the height, the highest and lowest part of my sine wave. Now what I'm going to do is I'm going to change the amplitude, and I'll use a different color to do that. I'll use a little lighter blue, and I'm going to make a new graph which is going to be 2 sine of x, which is now going to raise the volume of my graph by 2. So I multiply each of these points by 2. So 1 would then be 2 units tall. 0 times 2 is just back to 0. -1 times 2 is down to -2, and then back to 0 again. So this light blue line represents an amplitude of 2, even though the highest point would be a positive and the lowest point would be a -2. We can do the same thing, but it's a little weirder with negatives. Let's kind of compare this green line to the blue line. Let's talk about negative sine of x. And negative sine of x is going to be taking this graph starting at 0, and instead of multiplying this dot by 1, we're going to multiply it by -1. So even though it looks like ls, but this is technically a -1 sine of x, and we don't ever leave the 1 in front of it if that was your final answer. But this is to show you that this green line represents -1 sine of x. So there's your sine wave, your green sine wave, like so. Alright, so that's an example of amplitude. Now let's deal with period. We're going to use a sine wave again, and let's change back to blue here. And what I'm going to do is now consider this to be my 1 and -1 there. So here's my first graph here. There's my sine wave. Sorry, it's a little tall there on that side. Okay, so my sine wave is going to be like so. Okay, 2 pi. Now, what happens when we change the period in the problem here, like if this is sine of x, now what we'll do is we'll change the period, or the number of cycles, or the size of the cycle, I should say. I'm going to make this sine of 2x. Now what this is doing is it's making the sine wave faster, because we're not actually going like this in 2 pi. We're going to make this twice as fast. Now the formula for the period is going to be 2 pi over omega, and omega is the number in front of x. So what we're about to do is then take every single marking on this. So if, like this for example, is pi, we're then going to multiply that pi by our omega. Now, or by 1 over the omega, I should say. So the 2 is our omega in this case. So this is going to be pi over 2 is going to be your new spot for the graph. So this is going to be our new wave right there. So this is actually making the graph twice as fast, like so. So we get there twice within 2 pi instead of once. Now if I change this to a different color and say that my third graph here is going to be the sine, instead of 2 pi it's going to be half, or instead of 2x it's going to be half x, what's going to happen here is I'm going to go there in half the time. So it's going, or in twice the time, because I'm going to move half on my x here in this case. So it just means that between here and here I'm only going to go once, and the second half of it would be all the way under here. It'd take us to 4 pi to get to the same distance, because if my period is 2 pi and I'm traveling half speed, then my half would be in the denominator, and 2 pi divided by a half is the same thing as multiplying by 2 over 1, which is 4 pi. So I would make one cycle in 4 pi instead of just 2 pi. Now that's kind of interesting to think about when you actually look at these type of problems, these amplitudes and cycles or periods, without actually graphing. So for problem number 3, the amplitude is 3 and the period is just going to be 2 pi, because our number in front of the x was 1, and 1 times 2 pi is just 2 pi. Here our amplitude is going to be 1, because the amplitude is always the absolute value of the number in front of x. Because you wouldn't say that your amplitude is -1, because you are going above and below the same wave at the same distance. So we just take the absolute value just to make it convenient for us. Now the period though is not going to be 2 pi. The period is going to be 2 pi divided by 1/2, which is another way of saying 2 pi times 2. So this takes us to 4 pi. The period will be 4 pi, so this will stretch the graph out longer than it was before. Our amplitude here is 3, because we take the absolute value of the number in front of the problem, and our period is going to be 2 pi divided by 3. So this is going to cycle every 2 pi over 3, and which means it's faster. So it's going to be actually 3 times faster. It's going to get to it's going to do 3 cycles before it reaches 2 pi here, which that would be a little tricky to draw, but we're going to do that a little bit later on the graph paper. Now this is an amplitude of 4/3, and then our period is going to be 2 pi divided by 2/3, which is another way of saying 2 pi multiplied by 3 over 2. Doing a little simplification here, our period is going to be 3 pi, so it's going to be a little bit longer than 2 pi, but not as long as the one that we had in problem 4. Now, for this problem, the amplitude is not going to be any trick here. The amplitude is going to be 9/5. Now, it's interesting to see the negative in front of this, but according to our even-odd properties, we can actually just move the negative away, because the even-odd property says that the negative in a cosine is equivalent to just no negative at all, because we're dealing just with x values. So our period is going to be 2 pi divided by 3 pi over 2, which is kind of interesting. So let's change, instead of dividing by a fraction, we're going to multiply by its reciprocal, 2 over 3 pi. Pi's go away, and 2 times 2 is 4/3. It's interesting, we're going to make it there, and we would change our x-axis to actually not go by units of pi, but we'd go by whole number units, and that would be determining that. So for our last piece of the puzzle here today is we're going to look at some problems here, trying to figure out which function maps to one of the graphs there. And I'm going to use a different color for each one, and we'll do some process of elimination to do that. Let's start off with blue for this first problem. So it's a cosine wave that starts at 2. Now cosine waves that start at 2. Now a cosine wave, here we have A. Is a cosine wave that starts at 2. Let's look at all the other graphs. Here we have E is a cosine wave that starts at 2. Alright, so let's look at all the other graphs. Okay, so it's either A or E for problem number 8. And it looks like my period is pi over 2. So what we'll do is we'll take our 2 pi and divide it by pi over 2, which is the same thing as multiplying by 2 over pi. And if we simplify that out, the pi is simplified to 1. And then 2 times 2 is 4. So it makes one full cycle within 4 units, and that would be letter E. So 8 is letter E. Now what's cool about this is we can use process of elimination to kind of do some of the other ones here. So let's go to our next problem. So 3, this is going to be the light blue color, 3 cosine of 2x. So we're going to start off with a cosine that begins at 2. Cosine that begins at 3. So we look at our y-axis and see that the only waves here that start at 3 are, well, it looks like letter I is the only one, the only wave that starts is a cosine wave that starts at 3. So thank you, process of elimination. You were pretty easy, because this is a sine wave, actually a negative sine wave, which we'll talk about in just a minute. Alright, so moving on to another color, let's go with problem 10. Problem 10 is a sine wave that starts at 2. So let's look at all the sine waves that start at 2 here. That's a cosine. Here's a sine wave that has an amplitude that goes to 2. There's this is a negative cosine. This is a negative sine. This is also, hey, this is another sine wave that goes up to 2 and starts at 0 there. And these two. So it's between B and F. And now let's check out the period right there. So we're going to take our 2 pi, divide it by 1/2, which is the same thing as multiplying by 2 over 1. This is 4 pi. So which one cycles in 4 pi? It looks like this first one cycles in 4 pi. This one cycles in 4. So the answer for 10 is B. Alright, moving on to, let's keep the colors on the screen here. Let's move to a purple-ish color. This is a graph that starts, it's a cosine that starts at -2, so no, no, yes, possible. It's a cosine wave that starts at -2. Let's see, no, possible. Okay, we have another possibility here. Cosine wave starts at -2, and no. So between C and G, let's take a look at my period. This is 2 pi, and then let's multiply by, or divide by pi over 2, which is going to be 2 over pi. So this cycle gets finished at 4, and is it C or G? It is definitely G, because G finishes right there at 4. So this is G. And for our last graph, which will finish off the worksheet here today, let's go with a red color here, and our red color is going to be a sine wave that starts at -2. So this is or goes down to -2, so this is a possibility, and there are no others, so D is our only one left in the picture. Alright, well, thank you for watching. Part 2 is coming up.